Welcome back to Let's Code. I'm Chris Biscardi, and before I show you what I'm about to show you, I have to warn you, there will be a lot of screen shake in what you're about to see. So if you get easily, say, car sick and things like that, maybe be a little careful with this one. That said, let's take a look at some post-processing in Bevy. Now this effect is layered on top of the noise land effect that we've already seen, that we've already worked on this channel. And you can see the chromatic aberration and kind of the screen shaking that's going around here. That is entirely a post-processing fragment shader. So when it comes down to it, the actual scene isn't really shaking at all in the 3D render. And we'll go into what's actually happening here. But what is going on is that we have a 2D image that the 3D scene is rendering to, and we're taking that 3D scene and we're applying chromatic aberration using some simplex noise for the amount of value that we are offsetting in each direction for each color. And we end up with this quite interesting shake. The screen shake is what I'm calling it. I don't know what to call it. I think that this would be really nice to have happen every once in a while, maybe just on the ship and not on the whole screen or something like that. But I'm quite enjoying working with this right now, and I want to show you how to achieve a post-processing effect like this. So first of all, it's important to note that we've moved from the world of 3D shaders into the world of 2D shaders here. And to do that, we're using the Material 2D plugin for a new custom material that we called a post-processing material. I've called it post-processing material because I started working on this by using the example code in the Bevy repo. So if you go to the Bevy examples shader postprocessing.rs example, then you will see a smaller example of a cube rotating around. And if you run cargo run with the release flag, because we want it to be performant, and example as post-processing in the Bevy repo, then you get to see this 3D cube that has a basic version of the chromatic aberration that we're using, or I should say the original version of the chromatic aberration that we're using. And the effect here is basically just taking each of the colors from slight offsets and just moving them out with their respective R, G, or B values. So back to the noise land example. We've added this post-processing material, which, similar to the other shaders that we've added, uses the high-level material APIs that have been implemented in Bevy 0.8. And in our setup function, we've gotten the size of the window and set that in an extent 3D. And extent 3D is basically something we're going to use to size an image here. So instead of rendering our 3D scene with our 3D camera to a window or to the screen, we're going to render it to an image. So we have to construct an image next. We do that using this texture descriptor because we're going to pass it in as a texture to the shader on the 2D camera material. So we've got a 2-dimensional texture, which means X and Y. There's also 1-dimensional and 3-dimensional. We don't have a label here. The size is the size of our image, which in this case is the size of the window, which we defined here in extent 3D. And once we have our image set up, we can resize it, which fills the image data with zeros, same as the example. And then 2 images, which is, if we look up here, mutable resource or mutable access to the assets database for image, which image is this, which if we scroll up, I believe comes from, and this image type, I believe, comes from the Prelude. It comes from Bevy anyway. Now that we have the image set up to collect the image from the 3D camera, we can choose to spawn in the 3D camera ourselves. So in this case, you can see the old 3D camera here, which was just a 3D camera bundle with a transform that was looking at the ship that we have moving around. In this case, what we've done is we've specified each of the fields that we need. We've created a camera 3D with a new clear color, in this case, white. We've specified the camera target, so where this camera is going to output, as the image that we just defined. So instead of rendering to a window or a screen or something like that, we are rendering to the image that we created. And then the transform here is the exact same transform we had before. So we still have our 3D camera. It's still looking in the same place. It's still doing the same capture that we have in the other videos. The difference is that it's rendering out to this image rather than rendering out to the screen. Now, when we're using multiple cameras, we can kind of combine them together. So we have to define which layer they are to define which camera gets precedence, I believe. I'm a little shaky on this. This is something I learned earlier today, so bear with me. But basically we have render layers where our post-processing pass is going to be the layer after the 3D camera. Then what we do is create a new mesh. So in this case, we're creating a quad with a width and a height of the window. So what we've just done up to this point is we have our 3D camera rendering our image to an image that is sized to the size of the window. And what we're doing here is we're creating a new piece of geometry in the scene that the 2D camera will be able to pick up that is sized the size of the window. And then of course we have to insert our post-processing material. In this case, I'm using time to do a lot of the simplex noise over time, basically. So we take the time in, we do the simplex noise calculation like we've done in so many other videos. But more importantly, we have this image handle, which is the image that our 3D camera is rendering to, that we're passing in so that we can access it in the fragment shader of the 2D quad shape, the mesh, so we can apply that however we want in the fragment shader. If we keep going here, we have our material mesh 2D bundle, which takes the quad that we just created and the material, which is the material, the post-processing material with the shader on it, and we put it somewhere. We also insert the post-processing pass layer. If you didn't catch that, this is the render layers layer construction that we had before. So in this case, we've chosen to make this layer, the post-processing layer, the very last layer. After we insert that component on our material mesh 2D bundle, we need something that can actually view the 2D quad. So in Bevy, if we use a 3D camera, it will be able to pick up our 3D shapes. If we use a 2D camera, it'll be able to pick up our 2D shapes and sprites and things like that. In this case, we need to specify a 2D camera. We set the priority of this camera to 1 because the default is 0. So the camera 3D bundle has a priority of 0 and will render first, whereas this camera has a priority of 1, which means it will render second. So we've got the indexes 0 and 1 for the 3D and the 2D cameras. And then we also insert the post-processing pass layer. This function, since we are going right by it right now, we've seen this before. It's basically just taking the time and passing it into the material. In this case, it's the post-processing material. We've done this in a bunch of videos already. I'm not going to get too much into it. And then finally, we have our post-processing material. Well, not finally. We still have to go over the WGSL script. We have our post-processing material here. We're deriving as bind group, and we're implementing not material, but material 2D for post-processing material. So material 2D has a lot of the same fields. So if we implement the default members here, you can see we've got fragment shader, vertex shader, and specialize. I don't remember offhand the two fields that are missing here. There's alpha mode on the regular material, and I think there's depth also on the 3D material. But otherwise, fragment, vertex, and specialize are all on both of them. But we can have the default values for those. So we specify the chromatic aberration here as the WGSL script. We specify that our source image is going to be a handle to an image, which is the thing we created earlier, that it's going to be a texture. And again, these are IDs here. So time is a uniform, which means it's a read-only value for that will get copied out to basically all of the processing nodes that we're using on the GPU. And then we've got the texture and a sampler. So these will get passed in with our image, or they will be our image, whichever way you want to think about that, which we'll get in our chromatic aberration shader here. So what we've got is the, I've called this standard material because I keep using the word standard material. Doesn't matter. This is our post-processing input. So we get time here. And as a uniform, we have the time or the material struct as our first binding or 0 binding. We get the texture, which is a texture 2D as our first binding, and we get our sampler as our second binding. And again, this is a fragment shader. So there's a couple of things that we get as arguments here. We're going to take the position and the Bevy sprite mesh 2D vertex output. Now, one thing to note here is that if I save, it auto formats and inserts a comma here. So I have to save without formatting in this file, just in case you ever try to recreate this and happen to have the auto formatting happening. Make sure that you don't let this get split up amongst multiple lines. But this import is a preprocessor statement, basically. So the Bevy sprite mesh 2D vertex output, which we have here under Bevy sprite mesh 2D vertex output.wgsl in the Bevy repo, defines what's getting put in here. So we've got access to world position, world normal, UV, world tangent if tangents are defined, and color if vertex colors are defined. We haven't defined vertex colors, so we won't have this. And I don't think we have tangents here either. But we will have world position, world normal, and UV. So that code basically gets copy pasted right there. So we get access to UV right here because UV is defined there because the code just gets inserted. X and Y are going to be the X and the Y of a regular square or a rectangle. In this case, we want to turn it into the screen position. So while we have X, Y in full, I believe, integers here, more or less, we have F32s everywhere, but we can think about these as being like pixels numbers. So we have position.xy, where this could be like 50 or something, and this could be like 72 or whatever. We divide those by the view width and the view height, which are the size of the window, and we treat that as UV. If I specify this offset strength statically, let me do that actually and show you what this does. So we can see if we have a static value for the offset, the R, G, and B are statically offset and not changing. So if the ship is over here, it looks one way. If the ship is in the middle, it looks more or less the same way, depending on the camera angle, right? And then on the left, it still looks like all of these colors are offset from the core shape of the ship the same amount all the time, which is kind of cool. It's a little chromatic aberration, but it's not really like intense enough for what I'm trying to do right now. So instead, what I've done is I've defined the offset strength here as a simplex noise 2-dimensional value. So we pass in material time dot 5, or we pass in the materials time and we multiply it times 5 to get a little bit more happening with it. And the other one is materials time 0, 0, 2. And then I multiply them by 0, 2. These are all magic numbers. They're just kind of like things that I thought looked fine. So use whatever numbers here you want. Just don't use whole numbers because you'll get 0 out of the simplex noise. Which brings us finally to how do we specify the color for each position on the screen? And we do that by using the function texture sample, which is from the WGSL spec. And texture sample takes the texture that we've passed in, so our image, it takes the sampler, so how are we selecting pixels from that image? It takes the coordinates to select the pixel from, and then after we do all of that, texture sample gives us back RGB, in which case we take R. So for the first one, we make it go up and to the right, basically. So we do positive X, positive Y. For the G value, we make it go positive X and statically on the Y, like where the model would have been. And then at 0, and we do positive Y for the B. So we get R, G, and B from the texture sample, and we do the sampling slightly differently in each location. So we've got the UV coordinates, so screen space coordinates, that is somewhere on our screen. And we're picking pixels for the R, we're picking pixels for the G, and we're picking pixels for the B for where these, for what these should be colored, basically. And returning that output color gives us the post-processing effect. So because we have the time going, again, this is constantly changing, right? The time value is, again, the noise that we're taking out of it. So that's why we get this screen shake, because the noise is going from -1 to 1, and we're applying that to pick the positions, which changes the position on the screen, similar to the way that we saw earlier when it was a static offset. The chromatic aberration for R, G, and B were always in the same spot at the same time. So if you look at our ship here, you can see like the red is kind of like going up and then going down, and then there's green and there's blue. And so we're getting kind of like 3 shakes for 1 here, which produces a pretty intense shake. And one that feels a little bit like disorienting, right? Like you just got hit. So I would love to use this as like an occasional effect. I don't think it really makes sense to keep going forever. It's quite intense, but hopefully you learned something about post-processing in Bevy today. And to give a little TLDR on the entire video here, we've got this camera effect, right? So we start off with our 3D scene as normal. We change the 3D scene to render to an image instead of rendering to the screen. We then take that image and we draw a quad that's the size of the screen that we want to output. And we view that quad with the 2D camera to show the final image. That quad importantly, has the fragment shader that does the processing for us on the final image. So we're basically painting a picture. We're passing that picture to the shader. The shader is doing whatever it wants. It could do this chromatic aberration thing that we're doing right now. It could do a pixelation effect. It could do blurs. It could do whatever we want it to do. It could slice the image in half, whatever. And then we take that image and we render it out to the screen, which is really cool. I think specifically the idea that like cameras can render out to like different targets. In this case, we have it rendering out to an image is incredibly cool, right? Like I think that maybe we could even use this as like a write out these frames to disk instead of using something like Nanu. And then we could lock the frame step and we could produce consistently the same image over and over, which is something that I feel like I haven't quite rectified from when we were working with Nanu. Nanu gave us a really kind of straightforward way to generate a series of images or frames that we could then turn into a video. And Bevy doesn't quite afford us the same kind of affordances or APIs. So I think that rendering to an image here and rendering at a fixed lock step could bring back the ability to control what the output looks like at a given frame, which could give us repeatable results for some of these more visual experiments. I don't know that I'm going to do this. I don't know that it's super important to me to have like extremely repeatable renders. I kind of like having them be slightly different every time I see them. I think that we could use it this way. And I think it's really cool that we get to, I don't know, it feels very modular in a way that lets us actually use the pieces in combination to affect a new result. And that's kind of what I really enjoyed and what I wanted to share today. So if you have an idea for a post-processing effect that we could try, leave it in the comments and maybe we'll give it a try. I'll catch you in the next video.